All right, hello everybody. This is Calculus 1, Casual Calculus, Explanation of Derivatives. What calculus is, or at least the most basic thing, most basic explanation of derivatives. Now, this is the beginning of calculus, right? I wouldn't say pre-calculus is, because pre-calculus isn't really calculus so much, just a review and maybe an incorporation of a few other features that kind of help to complement your knowledge in learning what calculus is. But anyways, here is, I guess the best way to start with this actually is just an example. So let's just say I have a function, f of x equals x squared. That's weird. This was working a moment ago, and this caret symbol right here should make this 2 an exponential thing, but I don't know why that's not happening. This text editor is messing up. That's x squared though. X squared minus 2x plus 1. All divided by x minus 1. Now, something you might see here immediately is, well, maybe not immediately. I mean, I don't blame you if it wouldn't be immediate, because it wouldn't be immediate for me either. It might take several seconds, but this x squared minus 2x plus 1 actually factors into x minus 1 squared. And then, of course, that value is divided by x minus 1. So you kind of see here, right, that x minus 1 squared divided by x minus 1 is simply x minus 1, right? So that basically means that this expression is equal to x minus 1. The f of x is equal to x minus 1. Now, what if I was to ask you, though, what is f of x at x equals 1? Now, you might be inclined to say that, okay, because this is equal to this, then f of 1 is just 1 minus 1, which is 0. And you would be pretty much correct. Now, actually, if I graph this function, x minus 1, you see that that's true, right? Right at 0, according to this graph, right at 1, I mean, right at x equals 1, y is equal to 0. However, if you take it as this original function, if you look at the first expression, then this doesn't make sense, because you have x minus 1 and x is 1, so you're dividing. See, this is a dividing sign. You're dividing by 0, and dividing by 0 is not allowed. So actually, we say that x at 1, or f of x at 1, I'm sorry, is undefined. It doesn't exist. And you might be wondering, why is this? Like, why is it undefined if I know that it gets really close to 0, and it does, and like, you would think that it reaches 0. But as it turns out, the reason why we can't divide by 0 is, I mean, you just kind of think about this, right? You might think that this is infinity, right? And it could be. I mean, I could kind of think of it as infinity, right? But then again, is 0 positive or negative, right? You don't know. It could be positive or negative. So for that reason, I mean, it could be infinity or negative infinity, right? 0 is positive or negative, but that's really undefined. We don't know. So, I mean, we can't say for sure what it is, right? Not to say that we don't know when we'll ever discover it, because we're not discovering what that is, right? I mean, it's undefined. It just doesn't make sense, right? I mean, as far as I know, I mean, it's not really a rational expression. I mean, it is rational because, right, you have this. It's a ratio, but not rational in the sense of, like, it makes sense. It doesn't really make sense. So, anyways, we say that f of 1 is undefined, right? But we can still say that the limit of this function right here the limit of this function, aka f of x, as x approaches 1 is equal to 0, right? And it's equal to 0, I mean, you can see clearly here because this expression is equivalent to x minus 1. So the limit of f of x is equal to 0 as x approaches 1, right? But it doesn't actually equal 0. It approaches 0, and that's the idea of a limit here, right? This is actually kind of relevant to what calculus is, and before I get into that though, I'll show you an example, a couple more examples of limits and how they're calculated. So let's just take this function as an example, right? Limit 1 over x, right? 1 over x as x approaches, um, let's say infinity, right? What does that equal? Now, if I look at this, I mean, you might know this already, right? Because it's kind of intuitive. If I graph 1 over x, I mean, look what happens to y, like, or f of x, or whatever, right? Y equals f of x. So look what happens to y, right? It basically touches the line, the 0, right? The line 0, but it doesn't ever reach that value until x is infinity, which never really happens. I mean, I mean, it's kind of, you know, confusing as to whether or not x actually gets to infinity, but I guess it doesn't. I mean, there is a more formal definition of infinity, but I'm not going to go over that now. I don't think it's really important. But you see that it approaches 0, right? Um, you know, I couldn't say this because I know that it gets smaller than this, and I couldn't say this because I know it gets smaller than that, right? So I just say that the limit is 0, right? The limit of 1 over x, f of x equals 1 over x, as x approaches infinity, is 0. Now, what about negative infinity, right? What if x approaches negative infinity? Then what's the limit? You can see here that the same kind of thing happens, right? It gets more and more negative, but this gets closer and closer to 0. Like, look at the y value, like right here. See, I mean, it gets smaller and, I mean, lower and lower magnitude, right? The absolute value of y, it gets lower and lower. So this approaches 0 as well. But then what gets a little bit more confusing is what happens to this as x approaches 0? What happens to f of x, 1 over x, as x approaches 0? Now, you can see here that if I do this from the right, this shoots up to infinity. But if I do it from the left, this shoots down to negative infinity. See, this is another reason. This is like kind of a graphical explanation as to why dividing by 0 doesn't make sense. Because right at 0, I couldn't say for certain whether it was positive or negative infinity, right, if I'm dividing by 0. So for that reason, we say that this is undefined, right? We can't say for sure. I mean, we can't really, like, it doesn't make sense. Like, both directions, right? You see negative and positive infinity, right? Negative infinity from one, positive from the other. It doesn't make sense. So it's just undefined. Now, what we can say though is that a limit of 1 over x as x approaches, see that plus sign means I'm approaching it from the right, is equal to infinity, right? Because, I mean, from the right, I'm going to the left, and you see what happens, right? It shoots up to infinity as it gets closer and closer to 0. Oh, I forgot 0 right here. However, if I'm approaching it from the left, from this side, it approaches negative infinity, right? So you see that that's the opposite right there. So I'm not really completely sure about this signage. You might want to review it just to be sure. Look it up. Which one is approaches from the left and which one approaches from the right. This is approaches from the right for me. Like, intuitively, this makes sense. I mean, it's really just semantics. It doesn't really matter. But I would just brush up, maybe review on that to be sure. If you're taking some kind of test or exam. I mean, just a disclaimer, I don't actually have professional certification for this, so really this is to help you view this from a different angle, maybe hear from somebody who's currently a student. I'm a college student, so I'm taking Calculus 2 right now, and this is what I already learned, Calculus 1. So hopefully this will help you at any rate. But anyways, continuing on from that, you see Actually, these lines right here, this is what you call a horizontal asymptote, right? It's like a line. Just in this case, it's at y equals 0 that just keeps going, right? It's this line that this function never quite gets down to. It's something you call, this is what you call an asymptote. And then there's also, that's a horizontal asymptote, and there's also vertical asymptotes. That's another kind of just a semantics thing that describes graphs, right? Describes the geometric properties of our function. So it's not particularly important for calculus. I mean, it is a good angle to view it from. I like calculus from a geometric angle. I think it really helps explain things. But at any rate, yeah, I mean, vertical asymptote, horizontal asymptote. So that's all that is. I mean, hopefully that's relatively clear to you what that means, what an asymptote is. Now, there is a third type of asymptote that you will learn about in pre-calculus called an oblique asymptote, and that's basically like the same type of line, but it's slanted. So it's actually could be represented by a function like y equals mx plus b, like just a, a line function, the function of a line. But I don't really think that's necessary to understand, understanding. I don't think it's kind of, it's unnecessary for me to go over that right now. We're talking about calculus. I don't think it's particularly relevant. So yeah, at any rate, that's what a limit is, right? So hopefully that's relatively intuitive to you. I mean, that as x approaches infinity, I mean, x approaches infinity or negative infinity, whatever. Um, I mean, if a function like 1 over x, right, as it gets closer and closer to infinity, this gets closer, f of x gets closer and closer to 0. So anyways, continuing on from there, though, let's say that I had some kind of function like y equals x squared. And I'm sure you're familiar with this, right? It's like a parabola. It goes down, it goes back up. And you can clearly see here that x at 2 is 4, obviously, right? Because 2 squared is 4. But what if I wanted to take the average rate of change between 0 and 2? Then what would I do? Well, as it turns out, well, you probably know this already. That's just rise divided by run, right? 4 divided by 2, which is 2. That's the average slope between 0 and 2. That's the average rate of change, right? Our average slope is our average rate of change, right? Those are the same thing. And if I drew a line between the point 0, 0 and 2, 4, I would call that line a chord. That's just a geometric description, but that's just what you call it as a chord. It's not really necessary to memorize, but I just thought I would mention that because it's something you do learn in an actual calculus course, right? And I would like to call this an actual calculus course too, but that's up for the professors and actual college graduates to decide. Anyways, so you see here that that's the average rate of change, right? 2 between 0 and 2. The average rate of change is 2. So, yeah, I can describe this algebraically as average rate of change equals y2 minus y1 all divided by x2, that's x squared, x2 minus x1. And that makes sense intuitively, right? Because y2 is 4, y1 is 0, 4 minus 0 is 4, that's this. And then x2 is 2, x1 is 0, 2 minus 0 equals 2, and that's what that is. And this is just rise divided by run. That's exactly what this is. It's rise divided by run. And that's how I could calculate the average rate of change, the average slope, and that kind of makes sense. Now, a couple other representations of this are just like delta y. We say delta y is change in y. So delta y is y2 minus y1, right? Delta x is x1 minus x2 minus x1. So delta anything is change in something. So this is really just change in y divided by change in x. That's just another representation. It's really just another set of symbols and formula. It's really just a semantics type thing. Anyways, though, delta y divided by delta x, right? Y divided by run. That's all we're talking about, and that's easy enough to calculate, right, as an average. But let's just say that I wanted to calculate the slope of a line that has the same slope as. Let's just say that I wanted to calculate the slope of the line, like right here, right at x equals 2. At the point 2, 4. How would I go about calculating the slope at one point? Now you see right here that if I use this equation, it doesn't really make sense because I end up with delta y divided by delta x when x equals 0, or delta x equals 0. And I can't divide by 0, right? That's illegal. So here's what's kind of magical about calculus. Here is something that doesn't seem like it should work, but it does. And it's kind of satisfying when you actually make it happen. It's like, it goes like this, okay? So we have this number called h, right? And h equals 0, but that's a secret right now. We're just going to say it's h. We're just going to say that it's some finite value, some value greater than 0, right? Some number that makes sense to divide, some number that makes sense as a denominator, right? So that being said, we say h equals 0 and delta x equals h, right? And we just use our equation, right? Average rate of change equals y2 minus y1 divided by x2 minus x1 equals f of x2 minus f of x1, all divided by x2 minus x1, and actually x2 equals x1 plus h, so aka plus 0, but that's the secret right now, right? So we'll say that it equals f of x1 plus h minus f of x1, all divided by h, right? Because h is our change in x. Now, let's say that f is x squared. F of x is equal to x squared. See what happens. So you see, all we did is we just plugged in these values um, into our function, f of x equals x squared. Let's just say that x1, or just x, let's just call x1 x, because I don't really like writing that 1 every time, so let's just do that. Let's just take that 1 out, and actually, why did I put f of x there? That's not f of x, that's just x squared, right? So anyways, you can probably see where this is going. X plus h squared, if you multiply that out, is x squared plus 2xh plus h squared. And then you subtract, of course, this value from all that, right? That's still as it was, x squared. Notice that you have x squared minus x squared, right? So that those cancel. Those are gone. And of course, this is all divided by h. But look what else cancels. H cancels. So you end up with 2x plus h, right? Because h squared divided by h is h, and then 2xh divided by h is 2x, right? Basic algebra. So this is what you end up with, is 2x plus h. But remember our little secret that h equals 0, so this is actually 2x. Now, actually, in that whole little secret mission to reveal what the average rate of change is at one point, right? To know what the slope of the function is with just 1 point, we have a specific word for this. We call this dy over dx. Actually, we call this the derivative of y with respect to x. That is the derivative of f of x with respect to x. That is the derivative, right? That, as a formal definition, is equal to the limit of f of x plus h minus f of x, all divided by h as h approaches 0. So that's basically saying that as our change in x approaches 0, right, as we get closer and closer to dealing with just one point, then, well, we get closer and closer to our instantaneous rate of change. We get closer and closer to our derivative. In the case of x squared, we get to 2x. So, long story short, what this basically means is that any point in this function, right, x equals 2, I know that my slope is 2 times x, which is 4. So right here at the point 2, 4, I know that my slope is 4. I don't know about you, but I think this is kind of cool, right? We can calculate what the slope is for any given point of the function. So our function that we call the derivative would be 2x, right? And that's what that line looks like. So this is the relationship. See, like, notice that as this line is very negative, right, this function is decreasing, and as this line is positive, this function is increasing, and it increases faster and faster. So you see that this kind of makes intuitive sense here. Now, let's see here. So that's the formal definition of a derivative, right? And 2x is the derivative of x squared. And you could do this, you could carry out the same procedure with virtually any polynomial, x cubed, x to the fourth, x to the fifth. But when you start doing other functions, you'll notice that it isn't quite sufficient and that you'll need to use a slightly different procedure to find what the instantaneous rate of change is at any given point of your function. Now, actually, geometrically, again, we called this a tangent. Actually, this would be our average rate of change, right? Between 0 and 4 is the slope of this line, which is 2, right? The rise is equals 4 divided by 2, which is 2, right? That's what we talked about earlier. This is what we call a chord, right? I mean, like I said, you don't have to memorize that, but that's just what this is called. Now, a tangent line, actually, I mean, I didn't define that yet. A tangent line is the rate of change, a line that has the slope of the rate of change of your function at any given point. So here's what this looks like. It's better to show you this than to, just keep blabbering on about it, when you don't have a picture to go by. So y equals x squared, right? And this means that our derivative, we figure this out, is 2x, right? Now, if we're trying to find the slope at the point 2, 4, then we just take our x value, which is 2, and multiply that by 2, right? And then we get 4. So actually, the slope of our derivative, or I'm sorry, the slope of our tangent line, the slope of this line, line at the edge of our function that shows the instantaneous rate of change. Here, I'll show you. 4x, right? That's our slope. Now you see that, I mean, here, I'm gonna change this a little bit just to make it more clear exactly what's happening here. So let's see. I'm going to do a little calculation in my head. So yeah, right, like that. Okay, so you see what happens, right? At the point 2, 4, we have this line. This line, the slope of this line is instantaneous rate of change. So this makes it pretty clear what the slope is at this exact point. And this is what we call a tangent line. And you'll have some calculus courses that will ask you to calculate these. And they're not that hard to figure out, right? Because you know that the slope of this line is the same as the slope of this line, right? At this particular point. So the slope in this case, is 4, right? Because the derivative of y equals x squared is 2x, and 2x at 2 is 4, right? So the slope is 4 right here. So the slope of this line will be 4. However, it's not enough to just know that the slope of the line is at 4 to get a nice line at the edge of your function like this. Y equals 4x. If you do y equals 4x, then that'll be 4 times 2, which is 8. So you have to subtract a certain value from that, and that value happens to be 4 to get this value at 4, right? To get this line to match up with this line to have the same value as y equals x squared right here. So anyways, that's what a derivative is, right? Derivative is the instantaneous rate of change. It's the slope of a function at any given point. It's the limit of f of x plus h minus f of x all divided by h as h approaches 0, if you want to be fancy about it. Now, in some circumstances, actually, I was going to talk about more geometric implications of this, but I think it helps to understand integrals, so maybe I won't go over that yet. But at any rate, I guess that just about sums up what the derivative is, right? So hopefully you all get something from this video. God bless, and good luck with calculus. Hopefully this helped, and hopefully it helped you view the problem from a different angle if you don't think it's going to be your flat out, main calculus course. See you next time, and have a good day.